Now let's look now at the Monty Hall puzzle. Okay, to review, you've got there's a game contestant that has 3 curtains, and what they do is they choose, like, say A, B, or C. So the contestant chooses one. Choose one. Say that they choose A. Choose one. Say A. Then Monty Hall reveals what's behind one of the curtains. Okay, so let's say if you chose A, the contestant chooses chooses A. Then Monty Hall shows, say, C. So, and let's say that there's a bar of soap. So you know that there's like a prize, say $1 million behind one of these curtains. And so the contestant can either stay put, stay with A, or switch to B. And you might think, well, if someone came in off the street, they'd say they could choose either A or B, and it looks like there's no information extra, so they would just say, okay, well, it has to be 50-50. So one thought was, it doesn't really matter. And that's what the game show hosts and lots of people thought that didn't really matter, but it does matter. And let's see how we can do that. Now, the idea here is you have 2 different calculations. You want to compare the strategies of staying and switching. So let's say that we want to know what's the probability. Let's say the probability of winning when you stay. Well, let's say that what you want is the probability of a win when you stay. Okay. Well, I think maybe it's better to put it the other way around. This is sort of the stay probability of winning. Well, we can divide it. We can say, well, the person's made a choice, and the first choice is either right, that is, they win if they stay, or wrong. In other words, their first choice is either right, that they correctly have identified this. Well, let's say it's right that the prize is behind that window. Prize behind other window. The prize behind other window, or curtain. I'm not sure why I'm saying window. Okay, prize behind curtain chosen. Okay, so let's call these right R and W. No, let's call these, I don't want to use W for winning and wrong. So correct and incorrect. The first choice was either correct, the person guessed correctly, or it was incorrect. Okay, so we can, those are 2 mutually exclusive choices. All the possibilities are in other words, that there's, so this is, so that if you think of all the outcomes, either win or lose, This is on the first choice. Your first choice was either correct or incorrect. So the probability, given that you're going to stay, of winning is going to equal the probability of winning given that your first choice was correct times the probability it was correct plus the probability you win given that you were incorrect times the probability that you were incorrect on the first choice. Well, let's see what that is. So if and this is given that you're staying with your original choice. So if you're staying with your original choice, your probability of winning, given that you're staying with your first correct choice, is 1 times the probability that you're correct. Well, your only probability you're correct is 1/3 of the time because there's 3 windows. You choose one on your first choice. You have no information, so it's 1/3 plus the probability of winning if you're incorrect and you've stayed is 0. What's the probability that you're incorrect? Well, 2/3. So if you stay with your original answer, your probability of winning is 1/3. Now let's go and do the same thing, the same probability with the same partition of correct and incorrect for switching. Well, that's going to equal the probability of winning if you're incorrect, correct rather, on the first choice, times the probability you're correct, plus the probability of winning, given that you're incorrect in the first choice, times the probability that you're incorrect in the first choice. Well, if the probability of winning, if you're correct on the first choice, but you switch, means you're switching from a correct answer to an incorrect answer. Because up here, see, if you're correct and you're switching from the prize answer to another joke prize answer. So your probability of winning, if you're correct when you're switching, is 0 times 1/3 plus, well, what's your probability of winning if you're incorrect? Well, let's look at this. If you're incorrect, that means the prize had to have been behind one of these things. But since Monty Hall has opened one of them, if you're incorrect on the first choice, you're switching from incorrect to correct. So in this case, if you're switching and given that you're incorrect on the first choice, your probability of winning is 1 when you switch times 2/3, which equals 2/3. So the probability of winning if you switch is 2/3, whereas the probability of winning is if you stay is 1/3. So the idea here is if you sort of try to think of it this way, your probability of being incorrect on the first choice is much more likely. It's 2/3 more likely than you being correct. So since Monty Hall has revealed one of the windows, you're always switching. If you switch, you're switching from 2/3 of the time an incorrect answer to a correct answer. So 2/3 of the time you're converting a wrong answer into a right answer. And only 1/3 of the time you're converting a correct answer into an incorrect answer by switching. So the staying put just gives you your original answer possibility of 1/3. So you always want to switch. And if people, this went on for 10 years and no one really understood, people would switch or stay. It was more common to stay because people thought that it was just good to stay with your original answer. So no one understood, neither the game producers nor the contestants, that you always wanted to switch. And that gave you twice the probability that you would win. 2/3 of the time is greater than 1/2. So most of the time you'd win. Now, if they had realized that, 2 things would happen. Well, the game show would be over because there'd be no interest in, everyone would just, oh, I'm going to switch. So there'll be no uncertainty or no drama in it. And then and also the 2/3 of the time they'd win, so that the people running the show would have to have many more prizes available because many more people will be winning. Okay, well, that shows you how you can use conditional probability to understand this. It turns out that there's an interesting history behind this puzzle, in the sense that before this was understood, there's a column in the New York Times under the name of Marie Van Zandt. And what happened was that she presented essentially this analysis, maybe not using conditional probability, but she presented the analysis that if you switch 2/3 of the time, you would win, even though it looks like it doesn't matter, and that 1/3 of the time you would only win less than that. So the problem is that lots of people wrote in saying that Marie Van Zandt was wrong. Marie Van Zandt it's like a collection of people. It's just the persona of the account. But they wrote in, even mathematicians would write in saying this was incorrect because they didn't have a good understanding of conditional probability. So this is actually an interesting case in which that occurs. If you go online, you can look this all up on the Monty Hall problem. Okay, so there's lots of explanations of it, but there's a whole solutions using conditional probability and other kinds of solution. So there's all kinds of solutions, and here's maybe I missed, not Marie Van Zandt, but Vazant, and the media furor. So this probably this is the most interesting thing of the situation. And here's the paradox. So it's worthwhile reading this because you sort of see it's something in public. Now this actually, although this just seems like an entertainment situation, the actual problem that this occurs for, or is something similar occurs in legal situations in which I think this actually occurred in a legal case in which there was a crime, and a witness to the crime only had a partial plate. They only knew some of the letters of the license plate. And so the police then arrested someone who was in that area that had a plate with those partial with the partial plate. And the problem was that a statistician showed, or someone who understood the conditional probabilities showed that the probability that someone had with that partial plate in that area was quite likely. So it gave, just the fact they had the partial plate was not at all an indication that this person was actually committed the crime. This, of course, was a person that didn't have an alibi because they were driving in the same area and there were other issues. So the problem was that this was sort of thinking that the partial plate was giving you a false sense of the likelihood. It was a failure to understand conditional probability and what it actually meant. Anyway, so, and it's the same thing with we can also go on later and because we're out of time right now, and see that if you have a low probability event, for example, it's a relevance of knowing, say, if you take a test where there's a low probability that you like if you have a probability for a disease, that you may hear that a test is 99% accurate. The problem with those tests is that because it's very unlikely that anyone has the condition, say if it's like most people don't have COVID or whatever, but the problem is there's a huge population. Because of that huge population, you get a huge number of false positives. So it's really important to understand some of these issues, because even if you get a say a positive result for one of these tests that's 99% accurate, it can be quite likely that it just means you're part of lots of the people that are a false positive, because it's if you have anyway, so there's all kinds of, it's much more, if it says as a negative that you don't have that disease, anyway, there's all kinds of situations where this is important in taking tests where there's a low probability that the person has the condition that the test is testing for, even if the test seems very accurate. Okay, so we can go and talk about that later because we're out of time. and let me